Alright, I got a fun one for us today. This is a new set of slides, and we will not get to all of these topics on this title. There's even one hidden topic that did not make it to the title that we will get to today, but yeah, I think let's just get started. That's the best idea. So I want to talk about searching first. The idea of searching in a program is when you have something that you want and you're not sure if it's there. So like a vector, for example. You got a big long vector from somebody, and you'd really like to know if somewhere deep in that vector is the number 42. That's a useful concept, right, to go and want to search for it. And searching is universal. It does not have to be like vectors only. It could have been like, remember linked lists? Maybe you want to go search through a linked list and see if there's a 42 somewhere. Like, there's a similar process. There's similar algorithms, and I'd like to talk about them. So linear search is the most general one. So let's start with that. So linear is like line is going to mean something in a second, but this is like the most generic way of searching through your vector, let's say, to find something. If you're looking for a certain value, linear search is an algorithm that just checks everywhere. So like if this is your vector, eight, 6, 7, 5, 3, 0, 9. At all these indices, 0, 1, 2, 3, 4, 5, 6. Maybe you have some value that you really want to care about and see if it's in there. Val to search for. Like if this is your setup, maybe you want to look for 3. An easy way to find it is just to loop through every index and see if you can find a 3 at one of them, right? Because you have no guarantees about where things are in your vector, you just kind of have to search everywhere and hope for the best. And that is called linear search, checking every index from left to right. It's like you're going in a straight line. Going in a straight line until you find the thing, okay? It may happen that you don't find the thing. It's like maybe you're searching for 42 or something. We'll get to that. But like here's the setup for linear search. It's you give it a vector, can't mess with it, so constant reference, and then the value you're looking for. And then your job is to give back where you found it, the first place where you found it. So like the 3, finding the 3, you give back 4, the index where you find it. If you were looking for something that's not there, like let's say that the value we're looking for is 42, then you go through the entire vector, sadly you don't find it, and you'll return the fact that you didn't find it. You could have thrown an exception, technically, that's one way to do this, but one correct way to return a value and notice that there was not anything is to return -1, because that's an index that is invalid. It cannot exist in any vector. So that's a good number to use there. So just return -1 if you don't find the thing, okay? And I want to say that if you have no guarantees about the way that your vector is arranged, you can do no better than linear search when you're looking for something. I hope that makes sense. Like it could be at the start just as easily as it could be at the end. You have no clue where the thing is. You got to look everywhere for it. So yeah, let's make a linear search function, and then we'll turn it into a library, like a searching library with searching stuff in the searching part, and then like a main function that like includes our library and does fun stuff and uses it. So let's get that started. I'll call it searching.cpp. Boop. So, what do I want to do first? I guess let's pretend we have things. Let's be like vector. Let's make the one from the example. And here's kind of how I want to use linear search. Look through V for the number 3. Give me back the index where you find it. Look through V for the number 42. Give me back the index where you find it. Okay? So let's see if I can actually copy this today. Nice. Looks like it worked. And so linear search is all about just like start from index 0, go to the last index, in order, in a line, try to find the thing. So go through every index from left to right, looking for val to search for. Or I guess it can stay like that. Okay. So first index, potentially all the way to the last index. And like if you ever find the thing, like if v at my current I is equal to the value I'm looking for, then I'm done, right? I found it. my job is to return an int, the index where I found it. And that is I here. Perfect. So if you find it, the if statement will fire eventually. You will have returned the index where you found the thing, and you're done. But if the loop continues and it completes, having never found the thing, then you got to say something down here. So if we got here, the for loop ended, never returning, so it never found it. If we got here, we didn't find it, sad face. And so we'll return an index that does not exist. So we'll return -1. And that should do it. So there I am calling it for 3 and for 42. And yeah, the 3 is at index 4, and the 42 is nowhere at all. Cool, huh? So that's a linear search. It's, I think, not too horrible, right? It's an idea that you could have thought of, I think. So yeah, it's the best you can do if you have no control over the order of your vector or array. This also works for arrays, of course. And so now let's make a searching library. So we can have a header file, searching.h, with the declaration of this stuff. And remember your header file guards, so you don't infinitely include yourself. And this one needs a vector because it's talking about vectors, so we have to include vector here. But we cannot use namespace standard. Remember that you cannot use namespace standard in a header file. So if you say vector, you got to say standard : vector to have it understand what you mean, because that's us not forcing namespace standard on the users who include this file, because it's going to be copied and pasted. You can never use namespace standard in a header file. But in the corresponding CPP file, you can do that all day long. So let's see what needs to go there. So we got in the CPP file, searching.cpp, we should customarily include our header file, and that's going to work very well for us here, searching.h. Because what does that give us for free? We just got vector included for us. That's beautiful. And we can use namespace standard all day long in a header file. It's happy. Doesn't have to be standard : there. What next? Yeah, and then the program with the main function that includes our library is this one. I'll call it main.cpp. So I don't need to include vector, I just need to include my library. Because that'll include vector for me. And then I can use it. That should do it. So there's the main file. There's the header file. And then there's the implementation file. They're all working together. I hope that makes sense. So there it goes, it's happy, and we can compile with just the CPP files, G++, all the CPP files, and call it, I guess I already called it searching, so we'll keep it that. And there it goes, same stuff. All right, so we got a library out of the deal now. That's beautiful. You can do better though. You can do better than linear search if you have control over the vector. You know something about it. So here's a setup for that. Let's say that we're playing a guess the number game. All right, I've told you that I'm picking a number randomly between 1 and 100. What is the best value that you should always guess first? What is it? If I'm saying I got a number between 1 and 100, to maximize your chance of winning the quickest always, you should always guess 50 first, right? Does that make sense? And why? Can you think of why? Whee! If you say 50, why? Here's 1, here's 100. Why is 50 the right answer here? Well, I guess the fancy way to say things, the fancy way of saying why it's right, is like you're hedging your bets, or maybe the informal way of saying things is that you're hedging your bets, right? Because you're not sure if the number is either over here or over here. If you had guessed like, oh yeah, the number is 10 or something, if I said no, it's bigger than that, do you see how like you still have all this way over here to look at? Like you would have been lucky if it was within here, if I said, no, that was too high. But if you guessed 10 and I say, no, it's bigger, do you see how you have 90 numbers left? That's disgusting. So always hedge your bets and get the least amount of numbers left. You should guess in the middle of your current search space, we say. All right, because if I tell you it's too low, that's okay. Then you know it's not over here. You've cut off 50 numbers. You have 50 left. You see that? That's perfect. So then if I said too low, like now you know it's between 51 and 100. That's your new range, and where should you guess now is the question. So here's the range again. You know it's somewhere between what? 51 now. 51 and 100. What will you guess next? The middle of that, for the same reason, right? You want to hedge your bets. Like, don't guess 52, because if I say it's bigger, you suddenly have like 48 numbers left when you could have just had 25. All right, so always guess in the middle of your search space, because even if I say, oh no, that one was too big, you've cut off half of it every time. It's getting the smallest and smallest as fast as it can because of that. All right, so this will actually turn into an algorithm, surprisingly. There's somewhere I'm going with this. Another similar process is like, maybe if you're like me, like when you take a shower, right? You turn the water to be as hot as humanly possible so it heats up the fastest, and then you turn the dial to be like right in the middle between cold and hot. And then you see, like, you test with your hand, like, is it cold enough? Is it warm enough? And then you'll just keep on playing that game, guessing in the middle of your search space for the shower temperature even. So this is something that you do in real life probably. We can apply it to code. It leads to an algorithm called binary search, where you still have a vector and you still have something that you're searching for, but you know something about this vector. If you want to do binary search, it means that the vector is sorted. All right, so you need that. It's a precondition. You must have that in order to use binary search, but then you can play the guess the number game on it. So let's have an example vector. Let's have it have 6 things in it. If you know that your vector is sorted, you can play the guess the number game on it. Even though you don't really know what's inside, you can just guess in the middle first, all right? Because that gives you some very strong guarantees about where things are. You just look at this number and like compare it to what you're looking for. You can chop off either this side or this side. Does that make sense? That's beautiful. All right. So yeah, let's say for example that the value you're looking for is actually in there, and it's 33. All right, so it's just like the guess the number game. The optimal strategy is to check in the middle of your current search space, and that will cut it in half each time. All right, so let's say that like you can't guess in the correct middle of this vector. Let's say that the middle, we take the right middle for this one. The first number we look at in this vector is the middle, the right middle, 42. We compare that to our 33, and then that tells us that because we know it's sorted, do you see how you can chop this guy off? You know that if it's anywhere, it's between here and here. You don't even need to look at half the vector now. If it was size 1 million, do you see how beautiful that would be? That's really nice. And now you have a smaller vector to go and look through. Okay, and you'll guess in the middle of that again. Right? All right, look at the 7. Compare the 7 to the 33. Oh, that was too small, so I need to guess higher. So that finally means that if the thing's anywhere, it's between here and here. Do you see how we've just zoomed in on it? And then, of course, the middle of that search space is the 33 itself. You'll find it in the next round. But that leads to a very efficient way of finding things. I guess we did just check 3 values, so this was maybe a bad example. But even if the number was 87 that we were looking for, we only need to check like 3 values. We would have found it just as fast. All right, so that's very, very optimal and beautiful. All right, so that's called binary search. It's binary because like bi means 2, right? And so like you're cutting off, you have one side or another side that you pick. So one of 2 choices. So yeah, that's what happens. Every time you make a guess and you check your guess, your search space gets cut in half. It halves each time. All right. So yeah, let's talk about the algorithm for binary search, because like the setup is the same. Just got to make sure you have the sorted vector. How do you guess in the middle? How do you code this? Let us draw again a vector. Same one. There we go. And let's be careful about the indices now. And let's say the value we're looking for is 55 this time. So with binary search, we want to just keep track of where we're looking. How much of the vector are we looking at right now? Where do we think it is? What is our search space currently? Well, at the start, it's the whole thing. You haven't looked at anything yet, so it could be at the beginning, it could be at the end. Like 55 could have been the biggest thing or the smallest thing. We don't know yet. So our entire search space, the whole vector is the entire search space. That's what I want to say. So like we set up a low index to talk about where the lower end of the search space is, and a high index to talk about where the upper end of the search space is. So low at the very beginning of this will start at 0, and high will start at 5. That's our search space at the beginning. It's just like, initially it's the whole entire vector, 0 to size minus 1. And then here's your process. You now have a search space, always. You'll keep on checking in the middle of that and updating it. Check in the middle between low and high. So our first guess, our midpoint of our current search space is, I don't like the way I'm writing that letter. I'll get there eventually. It's the average, right? 0 plus 5 over 2. Just do integer division, so that's like 2.5, so just 2. And so we'll look at this first. This will be our midpoint. Okay? And so there's that one. We'll compare the midpoint, 33 to 55, and then using that, we will reset our search space. One of the ends is going to end up needing to change. All right? So if what we notice is that the thing we're seeing in the middle is too small, we should guess higher. That means that our low index was too low. We should change it to be from there to there. Does that make sense? High stays the same. If the thing that we noticed was a little too small, it's low that needs to change. Does that make sense to us? So we just cut off half the search space. So if I redraw it, let's just to show the rounds of it all. So we compared the 33 to the 55. We noticed that, no, that was too small, so that means low was too small. Like the first place that it could ever be now, because we know it was too small, is index 3. So low goes to index 3. We just cut it all off. So low goes there. High stays here. And now the midpoint is that, as you would expect. And then we'll just go look there and be like, oh yeah, we found it. And give back the index. Does that make sense? So you only needed 2 checks to find the 55. Do you see how powerful that is? Especially when the vectors get larger. So that's pretty cool. Every time you make a guess and you check it and you change your search space, you have cut off half of your array. Over half. Sub-array, sub-vector. And so that makes it much, much faster than linear search. Okay? Let's see here. Yeah, let me just kind of walk you through that on one more time, just to talk about what happens if it doesn't find the thing. All right, and then we'll code it up. So let's say, here is my vector. I'll walk you through what happens when it doesn't find the thing. Because you still need to return -1 if you don't find it. How does it notice that it doesn't find it? All right, so at the beginning of time, let's say that we're searching for something that's not there. So like 12. So at the beginning of time, our search space is this. We've got low sitting there, high at the end. That's our search space. It's the whole vector. I haven't looked at anything yet. And then the very first index I check is 0 plus 5 over 2. So index 2 is the first thing that I check. This is my first midpoint. I'll call it mid 1. All right. And so I check and I compare 33 to 12. Oh no, it's smaller. The thing I'm looking for is smaller. So low doesn't change. Like if it's anywhere, it's between here and here. So if the thing that you see is too big, then you change your high index. Does that make sense? Like this, like the biggest place that it could be, the biggest index where it could be is up to there, index 1. Does that make sense to you? So that's what we're going to do to change it. And I'll draw that in green. So high needs to change to index 1. And so this is the new search space between the same low and like the new high. This is high number 2. This is our current search space right here. All right. And so we'll calculate the midpoint of that. The midpoint is 0 plus 1 over 2. So that's 0.5. Chop off the 0.5. So it's 0 is the second midpoint. This is mid 2. And binary search will look at that, compare it to what we're looking for, and be like, oh, the thing I'm looking for is bigger. So if it's anywhere, like the low was too small, well, it's got to be up there. So it's got to be between, here's our original space. We just looked at the one, it wasn't that one. So it's got to be between here and here, index 1 to index 1. See how it's changing? That's going to become our new low index. When we look and we see that something was too small, we change our low index because it needed to be bigger than that. If it's anywhere, it's to the right of that. This is my low 2, this is my high 2. So this is my current search space between here and here. And the midpoint of that is, of course, the same index, mid 3. We'll look at the 7, compare the 7 to the 12. All right, and this is where it's going to mess up. So we see that 12 is bigger. So that means, just in general, like, it's to the right. It's to the right, and that means that our low is too small. So we're going to move our low index. This is what's about to happen. All right, this is in general. When you see something too small, you move your low index. Like if this is your current search space between low and high, you look in the middle, you see the mid thing, and you're like, oh no, it's too small. So then you change your low index. Like the first place where it could have been was to the right of mid. So low equals mid plus 1 is what's about to happen. All right. And so what's our low right now? It's that one. Low equals index 1. The new low is going to be index 2, low 3. And that has just messed everything up. Do you see it? It's like, all right, the lowest index where the thing might be, my search space is between index 2 at the left side and index 1 at the right side. See how that makes no sense at all? So that's the secret, all right? So yeah, at the beginning of time, we originally, like, we looked here, we started chopping stuff off normally. But now, like, that involved moving these things around. Now we moved the low to the right of high. And that's how you notice when you're done. If they ever stop, like if low and high ever pass each other, that indicates that your search space is empty now. And you have not found the thing. You could not hope to find it anymore. All right, that's how you know to stop and return -1. All right, that's the last secret. But yeah, in general, when you see something smaller, you change your low. When you see something bigger at the middle, you change your high. It's like, all right, that was too big, so I've got to go down there. All right, it's the flip of this. So let's code it. Adding on to my library, though. So let's keep the header file. Let's call it binary search. Same exact setup. It's just we have to only call it when the vector is sorted. So binary search. Give it a body. Let's go. So all right, we got to set up the search space. That's the algorithm. So at the very beginning of time, low is 0, index 0, high is size -1. So now it's set up, and now the idea is we want to keep on looking at the middle of my search space as long as the search space is valid. So it's like, while the search space is valid, do the following. All right. And we know what it means for the search space to be valid. We'll change this in just a second. But like, while we have a valid search space, I'll keep it there for now. What do I want to do with my search space? I want to get to the middle of it. So what's the mid of it? The mid index is going to be low plus high over 2, the average. And the value there, I'll call it mid-val, is equal to just the thing at that index, that mid index. So this is the value I'm looking at right now. And then based on it and how it compares to val to search for, I'll change my search space. So if the value I'm looking for is smaller than mid-val, that was which example? So yeah, value to search for is smaller than the thing I see there. So it looks like maybe this example, this first example, or maybe not. This it was when we were, gosh, it wasn't the first one. It was 12. Where's the good one? Oh no, it was over here. Yeah, it was this one. Cool. So here, like we saw 33, but we're comparing it to 55. The thing we see there is smaller. So that means if it's anywhere, it's over here. So we're going to change our our low index to be mid plus 1. Like it wasn't at mid, it was to the right of mid. Does that make sense? So it's mid plus 1 for the low index, if that ever happens. So let's see here. Or no, I'm so sorry, I did it backwards again. No, I was wrong. It was supposed to be this one. the value that I'm looking for, sorry, is smaller than the mid value. I was just explaining this other one. Else if val to search for is bigger than mid val. Sorry if you're yelling at me through the screen. Yeah, I had it right the first time. So if the thing I'm looking for, val to search for, is smaller than the thing I see at the middle, that means I need to look to the left. Does that make sense? So that means my high index, my low is still over here, my high index needs to be mid minus 1. Okay, does that make sense? That's what needs to go on. Sorry, I had it backwards. So what I'm saying here is the value I'm looking for is smaller, all right? And the thing I see in the middle is too big, so that means my high index is way too large. I can only, like, if it's anywhere, it's to the left of mid. So I need to look to the left. And so that's going to involve changing my high index to mid minus 1, because we know it wasn't mid already. All right, that was this case. Like the 33 versus the 12, I'm looking for something smaller, so my high index was way too big. The biggest index where it could be is mid minus 1. Okay, there's that one. And then, this is the one I already said now, if the value I'm looking for is bigger, it's the exact opposite. All right, the value I'm looking for is bigger, which means I need to look to the right, which is going to involve changing low to mid plus 1. All right, let me show that to you. So again, we're looking for something that's bigger than the thing I see at the midpoints. I see something smaller. All right, so val is bigger, 55 is bigger than 33. So that means if it's anywhere, it's to the right of mid. So that means low is too small. Like if it's anywhere, it's over here. High can stay the same, but low is too small. Change it to be mid plus 1. See that? And that's that one. All right, so that's the other case. Look on the other side. And then else, if it wasn't too big, it wasn't too small, it was just right. So that means we found it. And our job is always to return the index where we found it. And so where is the index where we found it right now? This one, mid. It was at index mid. So that's what we return mid. All right, and that's binary search. Mostly, we still need to worry about, like, while the search space is valid, we can do this. Okay, so what does it mean for the search space to be valid? While low has not passed high. Yeah, it's okay for them to be the same. That just means that it's only between there and there. It can only be that index. But if they ever pass each other, where low is now somehow index 2, where high was 1, that's just wrong. All right, so while the search space is valid, that means we want to keep searching while low is less than or equal to high. That means it's valid. They can be equals, just low can never be bigger. So while low is less than or equal to high, we have a valid search space to look through. If, though, we ever end this loop, that means low passed high. It got too big, and that means we did not find it. So if we get here, low passed high, that means we didn't find it. All right, and I hope that makes sense. So yeah, that's the relevant code. If you get past there, we didn't find it, we have to return -1 to say that. All right, that is the full code. So I'll have to zoom out quite a lot for you to see all that. But there's your binary search. All right, I hope that makes sense, every piece of it. It's going to do the right thing. It's going to chop off half the search space each time. And so let's see that working. Let's see here. Yeah, we'll need the main file now, huh? So here in the main file, we're hooking in. We got the binary search now. It's in the library. Let's make a sorted vector and call binary search on it. We'll call it v2. What was my example vector? 1, 7, 33, 42, 55, 87. All right, so we'll search with binary search now. That vector v2 now for some stuff. What we do? We did 33, we did 55, and we'll do 12. Compile with both the CPP files, and I think it did it. So 33 is at index 012, 55 is 2 after that, so index 4, and then 12 is nowhere. It correctly notices that the search space became empty, and it gives back -1. Beautiful. So it's working, and binary search really shines with large vectors. So if you had a size 1 million vector with linear search, like on average, it's somewhere in the middle. So like it'll search through 500,000 things. But with binary search, you only have to search the search space a certain number of times. It has to do with how many times you can cut it in half. So that has to do with the logarithm. So here, the log base 2 of a million is the number of times you need to like cut the search space in half, the number of like iterations of your while loop's body. Oh shoot, did I do it wrong? I think there might not be an underscore. Yeah. So round it up. You only need to check 20 elements with binary search if the size is 1 million. Only 20 elements, rather than like 500,000 on average with linear search. You'll find anything within 20 checks for binary search if it's size 1 million. Is that not amazing? That is wild. You should always search with binary search if you can. It's much more efficient. Okay? So there are other things, just like guessing numbers and taking a shower, that use this kind of binary search process. Another one that involves code is calculating certain functions. So it just so happens that you can use a binary search style process to find the square root of a number. This could be how you create the square root function in a library. All right, I'll show that to you. But in order to like gain the intuition, I want you to pause the video and try this question. So let's say that we're searching for the square root of 49. Like the user tells us, I want to find the square root of 49, please. And we're going to play the binary search game by just making a guess. All right, let's say that we've guessed that the square root of 49 is 5. It's a bad guess, but like, how do you know where your guess is? It's like we make a guess that square root of 49 is equal to 5, and we can't call square root because like we are square root. We're trying to calculate the square root. How do we know that 5 was too small? How do you know that? All right, how would you tell if the guess was too high or too low based on this if you cannot calculate the square root? Do you see how you might do it? Oops. You can't call square root because you are square root. That's the cart before the horse problem. So do you see, though, that you could get a different equation out of this? If you squared, you could then check, hey, does 49, how does that compare to 25? Does that make sense? Then you don't need square root. It's like you just need to multiply. You could totally multiply inside of a computer. Do you see how that would tell you that 25, oh, okay, that doesn't compare to 49. That was a little low. So conclusion is guess higher. Okay, that's the secret. And so there is a way to do this. I will give you eventually a lab on this. And so you can just make a square root function, give it a double. You can calculate the square root of any double, give back the double, as long as it's not like less than 0, by like repeatedly making guesses. As long as you start off your search space that like in a way that contains, where do I want to say this? As long as you start off your search space in a way that contains the whole answer, just like this for binary search contained the right index, if it was there, we can do the same for square root. All right, repeatedly guessing. And so the secret is, at the very beginning of time, what's your search space? If somebody asks you for the square root of x, your guess for the square root of x, like what's the range, what's the low and high, where it could be, we'll just say this. It's between 0 and the maximum of 1 in that number. So like if the user asks you for what's the square root of 49, then you're like, all right, yeah, start off your search space. I don't know what the answer is for the square root of 49, but I know it's between 0 and 49. Does that make sense? That's a valid search space. And then the maximum is important because do you remember that the square root of numbers less than 1 becomes bigger? It's like the square root of, like it's not correct to say that the square root of 0.25 is between 0 and 0.25 because it's bigger than that. Oh gosh. The square root of 0.25 happens to be, that is 0.5. See how it got bigger? So that's not good. An easy way to fix that would just be like take the maximum of your number and 1 to solve that problem. Just like, all right, it's between 0 and 1. That's still a valid search space. Okay? That'll work. I hope that makes sense. So yeah, just in general, you'll make that guess. And so, for example, we are trying to approximate the square root of a number. And so like the square root of 1 is 1. So I'll remember that. And then the square root of 2 is like 1.4 something, so it's like up there-ish, kind of. I'll just try to remember that. There's 2. It's like here's the... Maybe I didn't draw this to scale. I definitely did not. Something like this. This is the graph of square root, right? Something like that. Just take my word for it. So, yeah, if we want to find the square root of 2, let's say that that's my idea right now. Here's the drawing I want to make right now. We're going to make a guess that, all right, our initial search space for the square root of 2 is between, the answer is somewhere between 0 and 2. Yeah, that checks out. It's really like 1.4 or something. It's really supposed to be like that ish. That's close enough, I guess. But yeah, so initially, that means your low is the number 0, right? What is the correct square root of 2? I don't know yet, but I know it's between 0 and 2. That's your low and your high. Does that make sense? That's your initial search space. And then forever, until your guess is good enough, then you're going to keep on checking the middle. Take the midpoint, see if it's close enough using this kind of comparison. This will be a lab eventually, so it's worth understanding this now and asking lots of questions. All right, so yeah, you'll just keep on checking that and seeing if your midpoint was close enough to the square root, all right, by squaring it and seeing if it was close enough to the original number, just like we were doing here. Not the square root of 49 versus 5, but the 49 versus 25. That's like a midpoint, for example. And so, all right, with my initial search space, like somewhere the answer is between 0 and 2, the midpoint of that is 1, right? So that's my first midpoint. Does that make sense? The first midpoint is 1, mid 1, and we'll say like, okay, 1 is my guess for the square root of 2, so I'll check that by squaring it, right? I'll check 1 squared versus 2. 1 squared is still 1 versus 2. 1 was way too small. Does that make sense? So that was a little too small. It wasn't good enough. It was too low. So my new search space, it should start, if it's anywhere, is above 1. See that? So that will become my new low. Do you see that? My new low, and this is my high still. So now it's between 1 and 2. Does that make sense? And now the midpoint of that is like 1.5, mid 2. You'll square that and check how close it is to 2. It'll be a little bit bigger, right? Because 1.5 squared is 2.25, so that was a little too big. And so then you'll be like, oh, then I need to change my high index. Does that kind of make sense? That's what's going to happen. Change the high index to be your old mid, high 2. Just like you change your low index to be your old mid there. So that's like low 2. It's like now it's between here and here. Now you'll try 1.25 next. That's between 1 and 1.5. Do you see that? And you'll just keep on cutting off half the space, and eventually you'll get to the true square root of 2, which is like 1.4-ish, and that's what it was supposed to be. But like you'll keep on replacing. If the mid square was too low, change the low. If mid square was too high, change the high. Make it the old mid. That's going to be the process, all right? And then you're done the second your mid is a good enough approximation for the square root, which means that if you squared it, compared it to your original number, like the difference is very small. That's how we compare doubles, right? So make sure it's close enough to 4 decimal places, let's say. That's going to be the answer. Does that make sense? That can be an algorithm. That's very similar to binary search. So, for example, square root of 2, like somebody says, your x is 2, calculate the square root of it. Here is, like on paper, in code, kind of what you would do. All right, so I drew pictures. Now let's write it out. So you always got your search space, your low and your high. You've got your midpoint of your search space, and then there's always like a check you need to do to determine where to move next, and that influences your decision on like how to change your search space. Decision. Okay, so at the beginning, if you want the square root of 2, the low, like where could it be? It's between 0 and the max of 1 and 2, so 2. So if the square root of 2 is anywhere, it's between 0 and 2. We know that. Then you've checked the midpoint. All right, that's your first guess for the square root of 2. So you check 1. And so it's like, all right, how do we know if 1 is a good enough guess for the square root of 2? Just see how close it is after squaring it to the number 2. And that is way too small, right? So our decision is guess higher. Does that make sense? And so that means that mid is a better low. So we'll make that our new low. high stays the same. This is my new search space. See how it's zooming in closer and closer to the square root of 2? Now the midpoint of that is 1.5. I'll check and see, hey, how good is that compared to 2? That's a little too big. 1.5 squared is bigger than 2, so I'll guess lower, which is going to involve changing my high index. That was way too big. Change it to be mid then. So low stays the same, 1 to 1.5. So you always just bring it on down. And then this one is going right here, 1.5, okay? And then what's the midpoint of that? 1.25. You'll square that. 1.25 squared, compare it to 2. That's a little too small, right? Because the real square root of 2 is 1.4 something. It's like 1.56 apparently. Oops. And our decision is guess higher again, which means that low needs to be the old mid. Low was too low, so make it 1.25. If I know the square root of 2 is somewhere between now, 1.25 and 1.5, you keep on zooming in to the answer and keep on playing this game. Does that make sense to you? That will eventually make its way to the real square root of 2 without ever having to first calculate the square root of 2. You're just doing squaring, which is just multiplication. That's beautiful. That is one way to make the square root function inside of a computer. I think that's really cool. So yeah, you can go many places with that. You can calculate a cubic function, like anything to the 4th power. You can do the same game as long as it's always increasing like this. You'll never miss it. That allows us to calculate the square root, that fact. It's very similar to binary search. Okay, so yeah, with that in mind, I just have one last topic for the day. It has to do with compilation. It's a completely different topic. All right, it's called makefiles. It's very useful. It has to do with compilation, so we have to review compilation. Remember this picture? I showed it to you a long time ago. I'm ready to show it to you again, and you'll understand it better now. All right, so a compiler is something that takes a single CPP file, a single program, and translates it to machine code or object code. That's the ones and zeros for that one file. Okay, so that's our one file. You give it one at a time to the compiler. So it is a little confusing because G++ is doing a lot of stuff for us, but we have 2 separate files in our current example for the day. We have searching.cpp and we have main.cpp. When we give that to G++, the compilation stage separately compiles each of them. Does that make sense to you? That's what's going on, all right? You get the ones and zeros for just those things, all right? So the compiler spits out like machine code for just the searching part, machine code for just the main part. So that's what you get. It's going to do it twice. And then we also use other libraries that are already pre-compiled, like IOStream, Vector, all those fun things. The last stage is linking. It's a separate process. Even though G++ does it all for us, it does compiling and linking together, it is a separate thing. So you got your individual files and pre-compiled libraries, you got your machine code ready, your object code, your ones and zeros. You then link them together in the linking stage, and that creates your final executable program. Right? That creates machine code that is runnable finally. Right? It's not quite runnable because like your main file needed cout or something. You didn't have that code yet. You have to link with that code. So that creates your /searching that you can go and run. Right? That's the final process. All right? So each one of these is compiled individually into object code, and then we link it together at the final stage with any like libraries that we're using, and that gives us a final executable file that we can go and run. All right? So that's what we've been doing. It was this, right? It's going to secretly, G++ will compile them separately, link them together, get rid of all the scratch work, and then we have something that's executable. It's all in there with the library stuff. That's the one-step process that's being done for us, but I have questions for us now. So is that the best way? Is now the question. There is a better way, I think. Because think about it. If you change just one file, the way that we've been compiling things, like let's say you've got x.cpp and y.cpp and z.cpp, and you just compiled this. Like you already got something called blah, but you changed one line of x.cpp. Do you see how, given what we know, you have to recompile y and z too? Like it's going to do that whole process on all those files, waste a lot of time, just to remake your thing, okay? Because what it's going to do is, like, when you say this, it's going to go and, well, it needs to recompile x for sure into machine code, the ones and zeros. into object code. It's called x.o secretly. And because we gave y.cpp and z.cpp, we also need to recompile them, even though that was unnecessary. Do you see that? Make the machine code for those again. Z.o. And then it gets linked together in a final executable, which I have lovingly called blah, with any libraries that are being used. So that's all coming together. But yeah, you just change x.cpp. Like, this is the only way we know how to compile. Like, it seems inefficient, right? To go and remake these y.o, z.o machine code files. There's a better way. All right. Like, no. The answer is no. That's inefficient. There's a way to do it yourself, to like make these .o files so that you don't have to remake them. It's called separate compilation. All right. So you can do that. You can use these object files as an intermediate stage by saying this to G++, saying -c for just compile only, please. So that's compile only. And that will generate, you give it just one file, it will generate the .o file for that one file, and it will put it in the file system. It will make that actual file. It won't delete it. So you can use it. All right, so that's all there. And then you can do the same thing for the y and for the z, and keep the old versions around. Does that make sense? That's what we can be doing. So let me delete the compiled file, searching, just with the code itself. Now I can do the G++ -c for like main.cpp. That makes main.o. See it there? G++ -c for the searching.cpp. That will make searching.o. See it there? And then you can link it together yourself later. Okay, that's the goal. So linking is fast, compilation is slow. So it's okay to have to relink things. That's kind of a fact of life if you change something. But recompilation, you can control that now with the -c. Does that make sense? So to link, you just say you give the .o files to G++, it'll do the linking for you. You say the -o, what you want it to be called. So that's what you do. You give all your object files. You do the -c to make the .o files first. y.o, z.o. So you do that, and then you link them. You link them together with G++ to make your final executable file that I'm apparently calling exec file name. That is the linking process. That's really fast. That's not the bottleneck. The compilation is the bottleneck. So it's best to do it this way, because if you just change one file, you only have to recompile that one file. Just reuse the old .o files from the other ones during the linking stage. All right. So yeah, I've made the .o files. Now, if I bring them together, G++, all the .o files, main.o, searching.o, call it what I want. Hit enter. It linked very quickly, and I got my answer. That's called separate compilation. All right. And the beauty of that is, now I can change something. Let's change main.cpp only. I'll add a new thing to search for. Let's search for 87. Okay? I have not touched searching.cpp. I've not changed the searching library, so searching.o is safe. I do not need to mess with that. I don't need to expend energy to recompile this. It's only main.cpp that needs to be recompiled into main.o. That's the one that I'm going to recompile, only. You see it? And then you'll relink all of them together with all the .o files. The new main.o with the old searching.o. You didn't need to change the old one. And there's the new result, index 5. That is key. All right, that's very, very important, because one day you're going to be working on a huge, huge project with millions of files, and it will take a day, at least hours, to compile everything from scratch. So if you change just one or two files, you only want to be able to recompile just those. Keep the other ones already compiled. All right, otherwise it takes hours before you can test your program with all those files. Okay, so that's unfortunate. So you want to do the separate compilation thing with the -c's to compile only, and then link all the .o files once you're done with that. All right. So it is like a multi-step process now. It is a little bit unfortunate. Oops. What have I done? ls. Because you got to like make just this one, make just this one, and then link them all together. That's a little tedious. I'll give you that. So there is a better way though. All right. It's this thing called a makefile. So you can get the best of all the worlds with this separate compilation and this linking separately with a makefile. It will automate this tedious task of like, all right, let's do the -c, let's link them all up. It'll do all that for you if you just give it a recipe for how to build the thing just once. You just need to say it once, and then it will remember. All right. So this is a new kind of programming language. Technically, it's the makefile language. All right. So what a makefile is just like it's a recipe book for how to build your program. All right. So what a makefile is, it is legitimately a file in the same directory called exactly makefile, by the way, called exactly makefile with a capital M, no extension. That's what it's called. It's legitimately just called makefile, where you put rules for how to build your things, like how to build main.io, how to build foo.io, the program based on those guys. Okay, that's what it is. So yeah, it just has little recipes for how to compile your programs. And I'll teach you this language. It's a new language, all right? It's the makefile language, and you can run it. You can run these rules to build your final thing that you care about. All right, so let me teach you like this syntax. So just for fun, let's do a peanut butter and jelly sandwich. All right, let's make a makefile rule for a peanut butter and jelly sandwich, because that's all makefiles are. It's just a bunch of rules, and here's what each rule looks like. It's always the name of something you care about. That's like your target. We call that the thing we care about, target. And then you give a colon, and then on the same line you space separate all the ingredients or requirements that you need to build this target. All right, and then it's a little old-fashioned. You have to tab over. It's not spaces. You have to tab over. Vim will do this for you. You tab over, and then you give as many lines as you need of steps to make your target. These end up being terminal commands. Okay, so yeah, let's do this. Let's do a peanut butter and jelly rule to practice. So pb_j can be the target name. All right, that's the thing I want. And then what do I require? What are my ingredients to make peanut butter and jelly? What are my requirements, my ingredients? Well, to make peanut butter and jelly, you need peanut butter, you need jelly, you need bread, you need a knife, maybe a plate, etc. All right, and then you'll tab over, and then you give your rules. You give your recipe for how to build peanut butter and jelly with these requirements. So it's like open the peanut butter jars. Peanut butter and let's redo that. Open peanut butter and jelly jars. Get 2 slices of bread. Yeah, and then you can continue that. You know how to do that. So that's what a makefile rule looks like. Name of what you're trying to make, your target, the recipes, ingredients, and then the actual recipe, using the ingredients to build the thing, the target. All right. The beauty of makefiles is, let's say you try to run this rule, it will go looking for peanut butter in your pantry or whatever, and if it notices that you don't have any, it will try to make peanut butter. It will try to go looking for a rule for peanut butter, and so you can give one of those. Like, all right, how do you make peanut butter? It requires peanuts and a blender, right? Potentially some salt. Then you tab over. It's like, all right, how do you build using these ingredients? How do you make peanut butter? You blend the peanuts, and then you put in a jar, hopefully. There you go. Now you have peanut butter. And then if it goes looking for something else, like it'll go looking for jelly, maybe you have jelly, it's happy. Go looking for bread too. Before it starts this, it makes sure that everything's there, and it will try to build it if it's not there. So maybe there's a rule for bread. If it didn't find the bread, how do you make bread, right? Flour, yeast, water, etc. But an easier recipe for bread is like the one ingredient to make bread is money, and then you can just go to the store. Go to store, buy bread. That is technically a rule, right? Buy bread. So all these together, they work together, and you can just tell the makefile, hey, I want this. It will go off and make sure you have these things, building them if necessary, using their own rules, and then it gives you what you want. All right, do you see how powerful that could be? So now you can kind of understand these. It's like, to build main.io, I require main.cpp to exist, and like here's the terminal command that uses the ingredient to build the thing. Do that same for foo.io. And then to make the final executable program, I need the .o files, and then you should link them together. See that? I hope that makes sense. So like that's the makefile in general. So like the thing that you want, colon space, ingredients, requirements, whatever you want to call them. and then you give a bunch of terminal commands to like build the thing. Eventually, you can have as many as you need in order to get there, but eventually, like, you should be making something of this name. It's usually that's the file name. Okay, so yeah, in general, like if you want to make main.o, what do I require? Well, I better have a main.cpp sitting around. And then what do I need to do on the terminal to use this to make that? G++-c main.cpp. That seems nice. All right, and yeah, you can eventually build up things like this, like just say what you want. Build me this prog thing, and it'll go looking for main.o and foo.o, and if it doesn't find them, it will run these rules to build them for you. It's really, really nice. All right. So yeah, this is a brand new language. Like the comments or number signs. It's not C++. It's the Makefile language, and yeah, it's able to build things for you. It's really cool, and it's able to keep track of like when things have changed. It knows how to build things in the most efficient way. So like if you just changed main.cpp, it will just only recompile main.o before it relinks. Like you can do that. It knows how to do that. All right, and it also knows how to make requirements if they don't exist yet. It'll go looking for that ingredient. All right, looking for a rule to build it. So that's pretty cool, and it's just a terminal command. It's called make, and you say make what you want. It's like make main.o, make the name of your target, make prog. It's just a make file. It's going to go looking for the make file, and it runs the right rules. Okay, it's called the make terminal command. So yeah, it's pretty cool. And yeah, if anything changed, it will rerun only the relevant rules to give you what you really wanted. Okay, so it's very, very powerful, very, very awesome. And I'd like to make a makefile for our library just to show you how cool it is, but I think that's enough for today. All right, so you try it with this style. I think you could make it work, and then you say make like prog, make prog, or make I guess we're going to call the final thing searching. Give it a try. I think it will be useful. All right, but that I think is where I want to leave us today. We've already talked about plenty. All right, so we'll come back in the next one and give a makefile for our library and just watch it be really nice and automated. You just have to say it once, give your makefile once, and then until the end of time, it will recompile it for you very, very quickly and efficiently.